Okay, so I'll say where we were last time, but here's where we were in the most recent of the several recordings that y'all have been watching to make up for the fact that we've been rained out. So it's been a week since I've seen y'all. Good to see everybody again. It's been a while. Okay, so just a reminder of what we were talking about. We're talking about the chain rule, and sort of our first foot in the door on the chain rule was this little story right here. Well, this is arguably our second point of view. Our first point of view was to view the chain rule as sort of a consequence of what happens if you take this equation that we established in the previous lecture and just divide by dt. View everything as a function of t, call it time if you like, and there you go. But as an interpretation, I like this point of view about intermediate variables. The intermediate variables in this scenario being x and y, and you can think about how changes in t can cause changes in z in terms of how those changes propagate through the intermediate variables. Right? And so, in particular, here let me color code better. You can think of propagation of changes through x as giving you this term, right? And propagation of changes sort of through y as giving you that term. And we broke down the details last time. Okay. All right, so and that's where we left it. So let's do an example. Here we go. Here's an example. So here we have same setup as we had on the previous page. Z is a function of x and y. But then notice x and y themselves are functions of t. And if altogether you want to know how do changes in t, propagate through x and y and cause changes in z, right, how would you compute that derivative? We'll use the formula from the previous page. Notice the formula on the previous page requires me to compute the partials of z with respect to x and y. Namely, these two derivatives, right? Partial derivatives. Then I need to compute the derivatives of x and y with respect to t. That's these two derivatives. And combine per this previously agreed to formula. So here are those derivatives individually. Easy partial derivatives. And combining them as we're supposed to from the previous formula, and we have our answer. Now, one thing to notice about this, we did not have to actually compute z as a function of t, right? I mean, that'd be kind of the brute force way to do it. That'd be the, I don't really like the multivariable chain rule. I'm going to try to bypass the multivariable chain rule and just turn this into a single variable calculus problem. I'm really good at single variable calculus, right? So we didn't have to do that. This is much more convenient and quick. I mean, the functions I need to take derivatives of are right there in front of me. Okay. Let me also comment on that along those lines. Do recall that I gave this long speech about this at the start of the term, but this is a class about ideas, not a class about answers, right? So if the question says, given this, compute dz dt, you have to infer. Right? Part of the purpose of the question is to make sure that you realize, hey, you know what? This is something that can be addressed with material from this course, right? Namely the chain rule in this case, and to then give me a solution that's, that uses material from this course. So if you were to just take these functions and, explicitly put that into there and explicitly put this into there and get z as this great big huge function of t, and then take single variable calculus derivatives using the single variable chain rule, well, you've bypassed the purpose of the question, right? And it should be clear that that's bypassing the purpose of the question, because in that bypass there is no multivariable calculus, right? So make sure to interpret questions appropriately on the exam, and if the clear intent, as in this case, I think if the clear intent of the question is to use the chain rule, then use the chain rule. Yeah, you had your hand up.
I was just going to ask you, so you always give us x and y.
I'm not going to always anything. Now, the only application that I've shown you here is how to apply the chain rule in the case where we know all of the functions in question. But, there are other applications, and we'll see some of these here and there. You can look at my old exam questions. Sometimes I give you maybe x as a function of t, and I give you how z is a function of x and y, and then I give you certain values, and then the question is, how do you compute dy dt, right? So the point is, no promises how it's going to show up, right? But this is just showing you how various ideas connect to each other, and yeah. Does that make sense?
Yeah.
Yeah, and you had your hand up, yeah.
So is z just a function of x and y? Or is it
Yeah.
x, y, and z?
Now, well, it depends on how you think about it. You can think of this function, the composition, right? So the composition gives z as a function of t. But the way z is given not as a composition. Z is given as this, what I'm going to circle here, indicating this function here, where z is a function of x and y. Yeah. Really, if you get right down to it, z, x, y, and t are variables, and they are variables that we use to represent inputs or outputs of various functions. And we're not really giving names to the functions here. Now, so this is a little sloppy. But it's sloppy in a very standard and very convenient way. So I'm going to stick with it. But you see what I'm talking about, though? Yeah. Cool. Okay. All right. So make sure to interpret exam questions appropriately. Now, here's a variation of the question. So what is? We just got through computing dz dt. What happens at pi over 6? Here we have to interpret. So what could this possibly mean here, this pi over 6? Well, notice in what's written down, right, derivative of z with respect to t, I'm interpreting here, in taking that derivative, I'm interpreting z as a function of t. So this, then, is a value of t. You should interpret it as a value of t. So that tells you that. That makes sense? Now, okay, so what? So what do you do? Well, one thing you could do, and I don't really encourage this, but I suppose you could do this, and this wouldn't even really be such a bad thing. You could take x as a function of t and stick that into here, right? And you could take y as a function of t and stick that into there. Oh, I forgot some x's. There's another x, right? You could plug in and turn this formula that we have for dz dt, which, it's arguably a little sloppily written in terms of different echelons of variables. And you could plug in and get everything as a function of t, right? Once you have everything as a function of t, you could then plug in and say, I am interested in when t is pi over 6. Everything's a function of t. I'm going to take this value of pi over 6 and plug it in for all of the t's that show up in this combined expression. Keep in mind I've plugged in for x and y, right? And evaluate. And that'd be one way to do the problem. I think a better way to do the problem, though certainly more convenient very often, is to say, well, look, if I know that t is pi over 6, why don't I just do this one time, plug in t equals pi over 6, and figure out what x is, and figure out what y is, and just go ahead and remember that, right, for my convenience. And then when I'm plugging in, I've got now values of not just t, but I have values of x that I can plug in, right? And values of y that I can plug in. And help me evaluate the expression. Now, in this process, you don't have to. You notice I didn't rewrite this formula for dz dt. I just left it as, well, it's an expression in terms of x's, y's, and t's. And yeah, it's a little sloppy, arguably. But for computational purposes, this is fine, and I encourage it. Ray, see one? Yeah. Mm-hmm.
Can we have x and y in dz to dt in that expression?
Yeah, sure. So this is, it's a little awkward, right? But this is just kind of a compact rewriting. I mean, if you were to plug in x is a function of t, y is a function of t, yeah, I mean that's arguably sort of more explicit, but it's just a rewrite, right? So getting this answer, I mean, we've used the chain rule. The chain rule has served its purpose for us here, and leaving it in a more compact form doesn't offend. Yeah, right. Okay. All right. Okay, now what if you have more than two intermediate variables, right? So here, we have this formula here for what happens if you have two intermediate variables. And notice that for each intermediate variable, there is a corresponding path and thus a corresponding term, right? Second intermediate variable, that gives a second path through which changes can propagate and thus a second corresponding term. Right? What's going to happen if you have a third intermediate variable? If there's if there's a W here. Well, that's just going to give rise to another path and then another term. Right? You get one term per path through which changes can propagate. Namely, you get one term per intermediate variable. So I hope it's no surprise that with all of these different intermediate variables, you get one term for each. Plausible? Yeah. Okay, now, here's a twist. What if there are other input variables? Right? Not just one input variable, but a bunch of them. Well, now I can no longer really ask the question, what is the derivative of z with respect to that one variable? If I say, the derivative, single variable sense, like I did here, here's a, the derivative, calc 1, dz dx. That assumes that in the composition, z is actually a function of that one variable x, and it's not the case here. Now, z is a function, if you compose, z is a function of a bunch of initial variables. So, what I can talk about, though, is the partial derivative. Right? Reasonable question. What is that partial derivative? And the answer ends up being surprisingly convenient. The partial derivative, don't lose sight of the fact that means that we're just going to hold all these other input variables constant. So these are not allowed to change. And once those are constant, we're back to the same picture we had before, pretty much. Right? The only difference is that, here, where I previously had written dy1 dx, because that was a derivative, a single variable calc 1 derivative. Well, now technically I have to recognize that there are these other variables that I am holding constant, and so that is now a partial derivative. Right? So that's the only difference, really. You can compare. See what this formula looks like. See what that formula looks like. And it's pretty much the same formula, except for we have partials there, etc. there. Everything else is the same. I think it's really plausible. Is everybody happy with that? Okay. Let's see an example. Here's a question. I've got a bunch of equations describing relationships between a bunch of different variables. Want to know what is that partial derivative? Now, notice in justifying this equation, it's very helpful to have that little diagram. I like to call it roadmap. What variables relate to what other variables in what way? What's a function of what? It can be very confusing, right? So I'm a big believer. Draw yourself a roadmap first, right? And so notice W is a function of, well, apparently P, Q, and C, all right? Right, and then notice P is a function of X and Y. Q is a function of X and Y, etc. Okay, so having this roadmap made, note the question was to find the partial of W with respect to Y. There's the input variable I'm interested in. There's the output variable that I want to measure the changes of. Notice that we have three paths corresponding, of course, to 3 intermediate variables. And that gives us 3 terms. Everybody happy? Okay. So notice the role the roadmap played here, at least in our sort of breaking down and trying to figure out how are we going to put these equations all together. By the way, I could have been more unkind in the statement of this question. What if I had not presented these equations all in a natural order, right? What if I had kind of jumbled those equations? Then it'd be really hard to tell what's a function of what. What are the intermediate variables here, and what? Oh, really easy to get confused. So a roadmap straightens that all out for you. So now notice that these partial derivatives are all easy to compute. Right? And plug in, and there you go. Okay, we've talked about multiple intermediate variables, multiple terms. We've talked about multiple input variables. It doesn't really matter. It just means we're talking about partial derivatives instead of regular Calc 1 derivatives. Okay. What if we have multiple output variables? Answer doesn't really affect anything. You get right down to it. So, for example, if I want to know how does this variable change with respect to that variable, okay, well, so that clearly I'm talking about a partial derivative because all these variables over here have to stay fixed, and I have certain intermediate variables giving rise to various different paths, and I can write down how those paths propagate. And notice that in this discussion, all these other variables here don't come up at all. They're just not part of the question, right? They're not really relevant. If I want to know the partial of Z1 with respect to XM, I don't care what ZP thinks. Right? Everybody happy with that? They're separate questions. I could ask a different question of, now if what is the partial of ZP with respect to XM, and then again I have, several different paths, and now what Z1 is doesn't matter. They're just several independent questions as opposed to somehow interrelated questions. Everybody happy with that? Okay, now there is a convenient bookkeeping technique. In this case, once you have all the variables fully considered, in order to write that down, I do need to remind y'all of something. I hope this is a reminder. If it's not a reminder, then let me show y'all something, and that is how to multiply 2 matrices. Just out of curiosity, how many people have seen matrix multiplication before? Quite a few, but not everybody. Okay, all right. So this is just a mechanical process. Now, a great question comes up. This process I'm about to show you, why is this the formula? And I'm not going to be able to tell you the answer to that question in this class. But those of you who are engineers and are going to be taking Math 216 next semester, probably with me, because I'm the only instructor, y'all will hear me expound at great length as to why this is the formula in Math 216. But here in Math 212, I'm just going to show you. And so view this as admittedly a little bit weird, but this is how it's done, and there's a great reason for it that I'm going to ask you to sort of take my word on. Okay, here's the formula. If one matrix is a product of 2 other matrices, if you want to compute an element, a particular element that is in the what I'm going to call the ith row of the product, and the jth column of the product. I'm going to compute that particular element. Whatever row number that is, take the corresponding row of the left matrix. Whatever column, jth column here, take the corresponding column of the right matrix and do a dot product. That dot product computes that element of the product matrix. Weird little formula. Again, there's great reason for it that we won't talk about here. everybody comfortable with this? It's just an algorithm? Okay. All right. So that having been observed, I claim that the following formula keeps track, encapsulates all. There's a lot of different partial derivatives I could try to address with the chain rule here. I claim that there are P times M different questions I could ask involved here, because there's P different variables I could want to take partials of, and I could want to take their partials with respect to M different input variables. So there's P times M different questions. And here they are, right? All the elements of this matrix here. And I claim we're gonna sanity check this and kind of look through and see some how this fleshes out with some examples. But I claim that if you take all these separate questions, all these separate partial derivatives that I might want to compute, assemble them as a matrix. Seems a little weird, but bear with me. That matrix, organized in this way, is the product of these two matrices organized in the exact same way. And let's talk about how they're organized. Notice that looking for partials of z variables with respect to x variables, notice that the output variables, z1 through zp, are, well, all the numerators there are z1, et cetera, as you go down the rows. Down at the bottom, all the numerators there are zp. All the different input variables, x1 through xm. Notice that in the first column, those are all partials with respect to x1, and then going left to right, at the right, all partials with respect to xm. Right? So it's a very kind of I don't know, if you were just an ultra organized person and you had all these partial derivatives just lying around randomly all over your room, you'd probably want to organize them in some way, and this might be a reasonable. I mean, it's extremely natural way to organize. You might reasonably ask, hey, why don't we transpose? Why don't we do it like this instead of that? Why do the output variables have to correspond to rows, and why do the input variables have to correspond to columns? Couldn't I do it the other way? Yeah, sure, we do it this way. In a parallel universe, you could do it the other way, but nobody does. So we're going to do it the way planet Earth does it, and do it like this. Is everybody good so far? Okay. So note, same organizational structure for, if you look at this matrix where the z's are functions of the y's, output variables correspond to rows, input variables correspond to columns. Now, likewise for the third one. And I claim that matrix multiplication, this wacky little formula that I showed you down here, encapsulates all m times p of these different partial derivatives. And let's just kind of write that down. Let's just see this happen arbitrarily. Let's start with that one there. Oh, let's see. I need that. Oh, yeah, I'm going to use purple here. Let's look at that partial derivative. Partial of z1 with respect to xm. Well, I think through all these different paths and, write down all the terms, products, etc. Notice that I'll be looking at all of these partial derivatives, the partials of z1 with respect to y1 through ym. Notice those are this row that we're going to be using in the matrix multiplication. Also relevant in this calculation, I'm going to need to look at the partials of all those y variables with respect to xm. That's this column that we're going to be using that matrix multiplication. And so, in fact, if you take green dot yellow, that green row dot yellow column in this matrix product formula here, you will reproduce exactly the chain rule that we have for that composed partial derivative. How convenient. right? And then, analogously, if you want to compute, let's say, the partial of ZP with respect to XM. All right, well, that's this one. And let's see here, all of these, the partials of ZP with respect to the various different Y variables are there. The partials of all the Y variables with respect to XM are there. Again, matrix multiplication, the exact dot product that you do in this matrix multiplication gives you the chain rule again. Anyway, it's pretty darn convenient. Now, just as a cultural note, we've motivated, I'll say, the chain rule here from a certain point of view. There is a different point of view by which you could say that this is really kind of the natural way to write the chain rule. Look how convenient look how compact it is. If you give names to these matrices, and by the way, the common name when you assemble all the partial derivatives of a function, all the output variables, all the input variables, organize them in the same way, we call that the Jacobian matrix. It's just a name based on a mathematician's name. This already quite compact version of a bunch of chain rule formulas could be compactified even further. How crisp is that? I mean, that's pretty compact, right? Notice here's another thing. It's really nice about this. Remember how when you were doing Calc 1 and there's a point of view that says, the big idea behind the chain rule is that you multiply. It's the derivative of that. Very commonly it's written as dz dy times dy dx, right? So chain rule says that when you take a derivative of a composition, you multiply the derivatives. Here, I am multiplying the derivative matrices. That's pretty cool. A couple other quick observations. Rows of a Jacobian matrix. Each row, and it just happened to notice, is a gradient vector. It's just how about that? Ends up being convenient observation sometimes. Right? Notice also the columns. Let's say, here we go. Let's look at that column. That's what you might call the partial derivative of the z vector. Let me write that down just to expand. That is the partial derivative of the z vector with respect to yn. So each column is a partial derivative of the output vector with respect to one of the input variables. Neat observation there as well. Okay. Alrighty, moving along. Let's see how we're on time. Okay. So here's a special case. Now, this is really just the formula on the previous page, but easier. Let me remind you, on the previous page, we had the z's were functions of the y's were functions of the x's, and we multiply the Jacobians, and the Jacobians are organized in this certain way. And number of input variables, number of output variables tells you about how many rows and columns. And by the way, make sure to get that straight. The input variables correspond to the rows or the columns. You've got to get that straight. If you get it backwards, if you effectively inadvertently transpose, everything's wrong. It's a crash and burn. It's just a fiasco. So make sure to get that straight. And this is really just a special case of that. Here, though, there's only one initial variable. So there's only one input variable. For this function, there's only one input variable, and therefore there's only one column in that Jacobian matrix. Okay. Then notice for the composition, actually let me circle that in a different way. For the composition here, G compose X. In that composition, there's only one input variable, and so only one column. Yeah. And then, of course, now there is, for this function, there's several inputs and several outputs, so we have a matrix there. Okay. Next observation to make is that's a velocity vector, right? The derivative of position x as a function of time, that's velocity. We have an existing geometric interpretation of that. Right? And there, by the way, there is a nice familiar term. Notice how everything previously, this is all highly algebraic. We're just relating algebraic formulas here, right? Algebra, as far as the eye can see. Until now, and now we have a glimpse, right, of hopefully a little bit of geometry. And likewise here. That's a velocity vector. Now, velocity of what? Okay, well, let's go back up to what we were doing. Let's look at this function here. Position as a function of time. That's a parametric curve. Right? We didn't go into this thinking of that as being we went into it as thinking of functions composed and there's only one input variable. But we can, if we would like, and we would like, in order to get some geometry on the page, let's think of this geometrically. That x as a function of t is a parametric curve floating around here in space. And it's too bad this won't quite all fit onto the page at once. This right here, the composition, is a parametric curve in the y space. Right? Y position is a function of t. Parametric curve, again, that's going to be some sort of curve floating around in that space. Right? So what we have then is a nice opportunity for how to interpret what this matrix is. This matrix takes a velocity vector. Hang on. So there in blue, remember that's the velocity vector for this parametric curve. Let me come down here. Takes that input velocity vector and returns to you this output velocity vector. All right, so let's say that again. The Jacobian matrix, previously up to now, we've been thinking of the Jacobian matrix as a bookkeeping convenience, right? The Jacobian matrix is a way to take a bunch of otherwise, pages and pages of formulas for how to compute the partials of various, compositions, certain variables in terms of the smaller partial derivatives. Lots and lots of formulas, very compactly, and so it's a bookkeeping convenience. Now we have a geometric interpretation of it. When you're composing with one input variable. In other words, when you have a parametric curve in your domain, and then you look at the resulting image parametric curve in the target, the Jacobian matrix is the thing that gives you the relation. It's the relationship between input velocities and output velocities. This is a really important interpretation, in my opinion, of Jacobian matrices. It's not just a bookkeeping tool. It takes input velocities and gives you output velocities. Let's say that a little bit differently. Scenario. Suppose I were at this point. Forget about the parametric curve. Suppose that I were at this point here in the domain. And I were to take off and start moving with that velocity. And I want to know what would this corresponding output velocity be. Well, Jacobian matrix will do that for you. Jacobian matrix times your input velocity gives you your output velocity. That make sense? Yeah.
On the previous page for the JF times.
Yeah.
Which of those is the Jacobian matrix?
Well, on this page, they're all matrices. What I am, the analogy that I'm considering here, and on the next page, how I would extend this to the next page is, let me just get rid of a bunch of stuff here. Is I would say, pretend like there's only one input variable. So x1 is the only actual input variable, and then I renamed it t. Right? Okay, well, let's do this on the matrices now. If there's only one there's no x2 through xm, then all of that disappears, right? And all these become t's. And then all of this disappears. And these become t's. So that's where that came from. Does that make sense? Yeah. And then this function, what? Oh my gosh, what I am calling f here, it's Jacobian being that. What I'm calling f there, that's what I'm calling g here. I mean, it's simply not possible to have certain letters of the alphabet always play certain fixed roles and never change, right? So sometimes what is f on one page is going to be g on the next page, and that's kind of what happened here. Does that make sense, though? Yeah. Cool. Yeah. So anyway, I'm a big fan. I hope you all will take this seriously, that you should think of the Jacobian matrix as the thing that you multiply by input velocities to get the corresponding output velocities per that algebra and per this picture. All right. Let's see. Let me do that. There we go. Okay. Now, here's let's kind of re-examine the chain rule. Previously, I thought of the matrix form of the chain rule as being hey, well, look, I mean, if you just organize things in this way, then look, everything falls into place, and we have this convenient way of writing a bunch of what would otherwise be a tedious mess of individual formulas in sort of one relatively compact, or here even more compact sort of a way. And so now let me give you a different point of view on this formula, right? Rather than thinking of this as just a bookkeeping tool, there's a way to think of this as actually being geometrically natural. All right, so here we go. It's going to hinge on this. It's going to hinge on interpreting Jacobian matrices as being things that take input vectors and give you output vectors. Input velocities give you output velocities. Right? Multiplication by the Jacobian relates velocities. And here we go. Let's consider this scenario. Suppose I have y's are functions of x's. Suppose z's are functions of y's. Okay. Well, then by composition, missed. Let's try that again. By composition, the z's are functions of the x's. Right? Notice also, if I were here and decided to take off and start moving with some velocity, that would cause the y vector to take off and start moving with some velocity. I don't know what. If you move the inputs, you're going to move the outputs. I mean, so there's going to be some velocity on that y vector, and then likewise, there's going to be some corresponding velocity on the z vector. Now let's just talk about how all three of these vectors relate to each other by way of the three different functions on the page. G, the Jacobian of G multiplies by x prime to give you y prime. Right, Jacobians multiply by input velocities to give you output velocities. Yeah? Everybody happy? Let's see here. Well, the Jacobian of f multiplies by y prime to get you z prime. I mean, that's just, again, that's what Jacobians do. They take input velocities, they give you output velocities. And the Jacobian of the composition multiplies by x prime to give you z prime straight away. We don't even have to, go with y prime in between. Okay, well, that's just three observations. Now let me write that down algebraically. Right? Jacobian of G multiplied by x prime gives you y prime. The Jacobian of f multiplied by y prime gives you z prime. Alternatively, the Jacobian of the composition times x prime also gives you z prime. Notice that these are the same results down here. Therefore, those calculations are the same. Everybody good so far? And notice that, by the way, I think this is a highly plausible scenario, right? I'm just observing. Look, if Jacobian matrices relate input velocities and output velocities, these equations are just observations that if x prime gives you y prime and y prime gives you z prime, then that's the same z prime. That's all it is, right? And yet, note the result. The result is that this matrix and that matrix multiply by any input to give you the exact same output. Therefore, those are the same matrices. Right? So what we had previously gotten to as it's just a bookkeeping tool. The fact that Jacobians multiply is algebraic coincidence, and a way to keep from having to write down too many formulas. It's algebraic convenience. Now we have a geometric point of view on it. This is just an expression of the natural fact that using x prime to give you y prime and y prime to give you z prime results in having started with x prime and computed z prime. It's almost the hardest thing about this is it seems too easy. So anyway, this is a kind of a geometric point of view. This is my favorite way to think about Jacobians. If you think about Jacobians as being a tool that they take in input velocities and give you output velocities, then the fact that they multiply like this is geometrically natural and, expected even. Okay. All right. Different point of view there. Okay, so let's talk about second derivatives. By the way, something I've been wanting to mention, and I forgot earlier, but you'll notice that sometimes I'll write these compositions kind of horizontally, whereas sometimes I'll write the compositions kind of vertically. There's no particular reason. I don't know. The book does it vertically in all of the examples that they did, so I guess I was kind of trying to mimic the book, but most books, when you're talking about composing functions, compositions are usually written horizontally. So anyway, the point is it doesn't matter. Don't look for any hidden significance or underlying meaning in whether I write it vertically or horizontally or vertically. It doesn't matter. Okay. All right. So here I'm back to vertical. No reason. Okay. Old scenario. Z is a function of x and y. X and y are functions of, now two variables, r and theta. Here's our little road map, right? Expressing what's a function of what as per these formulas. Yeah. Okay. We could reasonably ask for, let's just say, what is the partial of z with respect to r? So we want to know what is that partial derivative. There's the propagation through the variable x, also through the variable y, that gives us these two terms. Notice some of these partial derivatives are easy to compute, right? X is a function of r and theta. There it is. So that's easy, right? Y is a function of r and theta. There that is. So that's easy. Okay. And then notice now that I've used this notational shorthand. Y'all remember this notational alternative? You make a subscript. It's kind of like this is the Newton notation of partial derivatives as opposed to the more Leibniz-like notation of partial derivatives. Okay. All right. So next question. What if I wanted to take a second derivative? Right? Suppose I wanted to take the second partial of z with respect to r. How do you do that? What's the... where are the paths? Is it a matter of breaking down propagation of changes again? And can you really do that? Not immediately obvious how to proceed. Here's how I like to do it. I encourage y'all to do this. I think it's very convenient. Observe, and this goes back to an observation that we made a long time ago. This thing here, in fact, let me circle this. This thing here, because z was a function of x and y. Right? See it right there. Z is a function of x and y. What happens when you take a function of x and y and take a partial with respect to x? You get another function of x and y. So this also is a function of x and y, and I'm going to explicitly note that on my diagram. So I'm appending my diagram. Anybody on board so far? Likewise, z is a function of x and y. Take a partial derivative with respect to y. You got another function of x and y. So zy is a function of x and y. Okay. With this appended diagram, how do you take a second derivative? Just go ahead. There's no trick. Just do it. Just heads up. You got to make sure to pay attention. Don't forget that you got to keep track of. Wait a second. What's a function of what? And then just go ahead. Everything works out just fine. So anyway, I'm going to walk you through some steps. There are some things you do need to be careful about, but I'm a big believer. Make sure to append your diagram for your own personal sanity. Okay. All right. So by the way, you can see now why it is that I wanted to rewrite that as zx, is because then it looks more like a variable. I'm treating it like a variable at this point. And if I'm going to treat it like a variable, it's handy to have it look like a variable. Yeah? So a very convenient notation in a circumstance like this. Okay. Right. So we just computed that. All right. So the second partial that we want to compute, we're just going to need to take the r partial of that thing. How am I going to take the r partial of this product? I guess you could say we're going to use the product rule, but now here's a neat little observation that you can make. Remember, when you say partial derivative with respect to x, we're taking the partial with respect to r of something. Partial derivative with respect to r means I'm going to hold all the other variables on its level constant. So theta is a constant. That means that cosine theta is a constant. And so it factors right out just like a constant because it's a constant. Everybody happy? Diagram helps us with that, right? Realizing that theta is at the same level is what allows you to make this realization that will, and therefore I am supposed to view it as being constant. Okay. All right. Likewise, sine theta, constant, factors outside of the partial derivative. Okay. Let me recognize you won't always get that lucky. Sometimes, like if I were taking the second partial with respect to theta, then, now it's not a constant, and then you have to use the product rule, right? And so just write out the product rule just like you normally would, and then, again, just slowly and carefully proceed. Everything's going to work out just fine. Okay, but I like this as a starting example. Okay, now question. What is the partial of zx with respect to r? Here's what a lot of students do wrong. A lot of students will write, and let me emphasize this is incorrect. Right? But a lot of students will say, how about zxr? Seems like a reasonable thing to write down. Right? That doesn't even make any sense. Right? That says that we're viewing z as a function of apparently all of these variables all at the same time. That's not a thing. You can't do that. Right? You got to decide, which one of these are you talking about z as a function of x and y? In other words, one of the elemental functions inside the composition? Or are you talking about z as a function of r and theta, the composition through x and y? Those are separate functions. Doesn't make any sense to talk about z as a function of all of them. Right? So this makes no sense at all. You can't do that. It's just meaningless. All right, everybody happy? Okay, so can't do that. Okay, if you can't do that, what do we do? What you do is realize that zx is a variable, and you're taking its partial with respect to a variable, and you look at paths of propagation, right? So changes in r will cause changes in zx by way of these two paths, which gives you these two terms to compute that partial derivative with the chain rule. Anybody happy? Okay. Likewise, over here, partial of zy with respect to r. Well, there's zy, there's r. We have two paths, thus two terms to compute that partial derivative, like that. And now it's kind of all over but the shouting. And a little bit of details to work out here, but don't forget we know how to compute that partial. X is a given function of r and theta, so that's easy to compute. Partial of zx with respect to x, that really is zxx. That does make perfect sense. Z is to be viewed as a function of x and y, so there's no problem with that, right? Et cetera, et cetera. Don't forget about these extra factors in here and multiply it all out, collect some terms. It's just algebra, and you get down to this. This is sort of the most compact version of the answer you can get. Okay. All right, so good stopping point for today. See y'all on Friday. Have a good one. Oh, hey, I've got homeworks to return. Let me return those homeworks. Stick around for just a moment, if you would.
Yes, I might be happy. I'm not happy.